Well, I did not know that this classroom also has a microphone and a speaker system, so I'm going to give it a try until you guys all fall asleep. When I was taking a really boring computer science class, it's called file systems. So they didn't talk about anything except for file systems, and there was nothing interesting at the time. Remember, this is before NT, before Windows NT, and also before the Linux. Okay, I'm just adjusting the volume until it's just right. So it was really boring, and this is also back in the days when we do not have computer projectors, but we do have overhead projectors. Okay, I don't think many of you have seen the overhead projectors, the old style overhead projectors, where it's more like a light table and there's a lens system to project the image.
I've seen that.
And the professor liked to sit down next to the projector, slap on some slides, and then when he talks, he liked to make circles, circular motion with his pen over the projection area. So to him, it's not very, disturbing because it's just, kind of like circling like this. But it gets projected into the full screen, so we all see like a big pencil, circling around in big motion. And he has a really kind of monotonic kind of voice, much more than mine. Okay, so usually within 15 minutes of the class, about half of the class will be asleep. And remember, only half of the class enrolled class actually attend the lecture. And out of those people, half will be asleep like within 15 minutes. So I have to be careful when I use the projector to make sure that I don't actually end up with that type of problem. And that echo thing, you can hear the hum. I cannot seem to get rid of it. So I'm going to try a few things. Yeah, let's do here.
I think that hum was there last session too.
Oh, okay.
I think it has to do with the
feedback.
The ventilation.
Does it sound like a 60 hertz hum to you? 59 and a half, okay. Does anyone have absolute pitch, like when you play your musical instrument? No one has absolute pitch. Okay. We can find out what 60 hertz really is. 60 hertz key note.
It's just
well, can't find it that quickly, huh? Okay. Mystical. Musical.
It's like an icicle. I thought it was some sort of creature.
Maybe it doesn't really map to a particular tone, because I know 440 is A. So, okay, let's work on the math here. Hey, this is discrete math, right? And this is still math. Okay, 4. Yeah, it's problem solving for one thing, right? Okay, so A in the scale, or the middle part of the piano, A is 440 hertz. And with a scale, it's 1 octave is either doubling or halving the frequency. So that means the A that is below the middle A is going to be 220 hertz, and then the A below that is going to be 110 hertz, and the A below that is going to be 55 hertz, which is close to 60, but not quite, right? Okay, so now the next question is, how do all those tones work out in a scale? Like in a major scale, you have do, re, mi, fa, sol, and in a minor scale, you have the other ones. So as it turns out, there are 12 semitones from 1 octave to the next. Okay, but that doesn't mean that you divide
2 by 12 because it is a logarithmic kind of thing. So you have to take the log of 2, divide that by 12, okay? That becomes the step between each semitone in a musical term. So I think, so based on all of that, so I think, the 60 hertz hum that you're probably hearing right now is probably a sharp or a B. A sharp is exactly the same thing as a B flat. So I think it's either a B or an A sharp because it's really close. It's really close to A.
Is this going to be on the test? Is this going to be on the test?
Well, I have to cast it in a set first. So I'll have to ask a question and say this. This is a set of all the notes on a regular piano, and then do something. We'll do something about it. Okay. So remind me that I will ask a question like that. Well, it's all fun stuff. I mean, All right. So I think I signed in. Just need to go to this class and remind people about a few things. Okay, so we are getting into set theory. I did put out this self-assessment, which means it doesn't really count for your grade, which does not mean that you should just ignore that and not do anything about it. So you probably want to take the test and see how well you do in the test, because it might help point out certain concept holes that you might have, and you can ask questions about those. Occasionally, I put up the wrong answer as the key, and you can just say, okay, I have no idea what is the actual correct answer, because this one is not right either, okay? So give it a try. So we are now, does anyone remember where we stopped last time?
Finished after the Cartesian Products.
Okay, so right after the Cartesian Products. All right. So we finished all the intersection unions and stuff like that. So this is the Cartesian products. Say again? Okay. So the Cartesian product is, it looks like it's kind of funky and who would need to use anything like that. As it turns out, it is going to be very, very useful later on. Because when we talk about functions, a function is actually a set of tuples, okay? And as a result, you can look at it as a subset of the Cartesian product between the domain and the subdomain, or codomain. Domain and codomain. All right, so this is really just something that we will talk about further down the road. And then we have the self-assessment. The self-assessment is really just all about basic set theory, so there should not be anything that's surprising. So what I'll do is I'm going to preview the quiz. Yep.
No, there's like a beeping noise.
Yeah.
There's a beeping noise.
Now there's two of them.
That's the alarm of the next room. Either the next room or the room across on the other side.
So we're not going off. We're probably not going to die, right?
That or the alarm for.
Well, I'll be the first one. I think it's the alarm next door. Well, I'm going to do this. Can you hear me?
You can teach from out there.
He needs a warn your mouth, right?
I'm okay. Don't worry.
Hear this.
Still alive, walking back to the classroom. All right. So it is the alarm next door. I don't really have the disarm code for that room, so I would much rather not to get into the room, and then the police may show up and think that I broke into the room. So I think the police will come. The door is actually locked, so there's no real issue that I can see.
So it's like a security alarm, not a fire or anything like that?
It's a security. It's just somebody opened the door, did not know the alarm code, and decided to probably just, I have no idea. Could be a cat dropping in and trigger the alarm. All right, so getting through this stuff here, so I'm just going to give you the answer. And if you think the right answer is something else, let me know, okay? Because we will try to work it out. Okay, so U is a set of all even numbers, okay? Numbers that are divisible by 2. V is a set of all multiples of 3. So I just rewrite U and V, using the set notation. And the whole thing is I want you guys to kind of get used to the notation. So in this case, you read it as U is a set, because we use the curly braces, where in the set each element X has to meet 2 requirements. It has to be an element of Z, but this Z means a set of all integers. And X mod 2, or the remainder of X divided by 2, has to be a 0, okay? Because that means X is an even number. The other one is about the same, except we are dividing X by 3 and still want the remainder to be 0. So I want you to tell me what is in the set T, and T is defined to be the union, or intersection, is the intersection of U, V. Which of the following is an element of T? What do you think? It has to be something that can be found in both sets. So B is the correct answer. Okay. Let's move on. Yep.
What if it was union?
If it's a union, then all three. Then all three can be elements. Or all three should be elements, I should say. Okay, good question. Okay, next question, number 2. Let U be a set of just A, B, C, D, and V is the Cartesian product of U with itself. What is the number of elements in V? So this is kind of a trickier question because you do have to understand the idea of what is a Cartesian product first. So what do you think? 16 is the correct answer. Okay, very good. All right, very good, because it'll be AA, AB, AC, AD, and then BA, BB, BC, BD, and so on. Okay, and those will be the tuples. Next question. Once again, we have Cartesian products, but this time I am combining the concept of Cartesian product of 2 sets with the concept of a subset of, as opposed to an element of. So this time I have a U is a set, but U itself is the Cartesian product of the set 1, 2 with the set AB. So the question is, which of the following statement is true? Okay, so what do you think? The correct answer is B. B is the right answer. Okay. It is a little bit tricky because I give you several things that seem to be right, but it's not. C is incorrect because the tuple 2A is not even a set. And if it is not even a set, it cannot be a subset of something else. So that rules out C. B is correct because U itself is a Cartesian product. So that means its elements have to be in the form of tuples, or 2 tuples to be exact. And D is the only one that really fits the description, because if you look at A is basically saying a set AB is a subset of U. But U is not a set of individual elements. U is a set of 2 tuples. So just because of that, A cannot be the answer. And D is incorrect basically the same way. You can rule out D without even working the Cartesian product, because 1 individually is not a tuple. And U is a set of tuples, and that's why D cannot be the right answer. Okay. All right, so let's move forward. Next one. Okay. This one is asking if you let U be a set where you multiples of 2, and V is a set of multiples of 4. So what is an element of U minus V? Okay. Now remember, in the quote-unquote subtraction of sets, it means the resulting set will be the elements that can be found in U but not found in V. Okay. So A is the correct answer. Because 6 is a multiple of 2, which means it is in the set U. But 6 is not a multiple of 4, so it is not excluded from U minus V. Are there any questions about this? All right, let's move on to the next one. Okay, U and V are two sets, and this time I don't even tell you what are the elements of these two sets. What does it mean if U union with V is the same as U intersecting with V? They have to be exactly the same. Very good. Okay. So U and V are the same, but they have exactly the same elements. Now they can both be the empty set, okay? But if you look at C, you know, it is a more, it's still a correct answer, but it's more restrictive than it has to be. So that's why the answer is actually A and not C.
Can you go into, what do you mean by restricting? Do you mean like it's just not as
General.
okay?
It's a must, but it's not true.
Okay.
Okay. That's a good question. So is that okay? All right. All right. Moving on to the last one, question number 6. So in question number 6, I give you two sets, U and V. So I'm asking you, if I take the V minus U as one set, I use a union to union that with the intersection of V and U again. And again, I don't even tell you what is in U and what is in V. Which of the following is the correct answer? B is the correct answer. Okay, because it just comes back with the set V. There we go. All right. Any questions?
I think we should go over that one.
The last one?
Yeah.
Okay. So what you want to do is to first get what is V minus U. Okay, V minus U is a set all by itself with elements that you can find in V but not found in U. Is that okay? And then the other one, which is V union with U, are elements that can be found in both. Is that okay?
V intersect.
V intersecting with U, correct. So when you union these two, then you are adding back the stuff that you excluded from the left-hand side of the union to add everything back to V. Okay, let's look at the Venn diagram. I cannot do this using the projector, so you kind of have to write your notes. Just a few pictures. Okay. So let's just say that they are not disjoint. If they're disjoint, there's really not much to say. Okay, and I will give you that example as well. So let's just say that V is the one on the left-hand side, and U is the one on the right-hand side. V minus U would be everything that you can find in V, but not found in U. So I'm going to use horizontal lines to represent that portion. Is that okay? V intersecting with U will be the things that can be found in both, right? So that's the intersection. So I'm going to use maybe a different color. I don't think it's needed, okay, to mark the intersection. Okay. When you take the union, you're basically saying the union of two sets would be a set of elements where the element can be found in one or the other. Okay, not either, it can be found in both, but you have to be able to find it in at least one of the two. So when we take a union of the horizontal lines and the vertical lines, what do we get back?
V.
Exactly V. So in this case, the Venn diagram is actually quite useful because you can actually see how it is one piece of V and the other one is the other piece of V, but when you put them together, you get the original set back. Okay. Are there any questions about these 6 questions? Yep.
What was the answer for number 4 again?
For number 4, let's see. I cannot remember.
The ordering is shuffled.
It's number 6. It's 6. 6 is an element that is found in U but not found in V. All right. Are there any questions? Yep, go ahead.
What if those two sets have nothing in common?
What if they're disjoint? Okay, so if these two are disjoint, so you have V sitting somewhere, and then you have U somewhere else. Is that okay? So that means, so let me switch back to that question so we can see the context of the question. So in this case, we have this being V and this being U. What is V minus U? What is the set consisting of elements that you can find in V but not in U? Just V all by itself, right? What would be the intersection between these two? It's an empty set. So when you union V with an empty set, you get V back. So it is still the same answer. It is just V. It's still the same answer even though these two do not intersect anymore. Okay, good question. Yep.
I think this is kind of a silly question, but V by itself, like V right there, and the set V plus the empty set are identical, right? Like the empty set
That's
is not
correct.
an actual element.
Given any set, X itself can be an empty set, but it doesn't have to be. Anything that is unioned with the empty set is just the set itself. In other words, if you look at an empty set like 0, union is kind of like add. So it's the identity with respect to union. All right. Any other questions? That was one more hand. Yep.
What was the answer to number 1?
To number 1. Yep, because it's an element that can be found in both.
6.
Yep, B. But yours may not be B because it scrambles. Yep.
I had a question about number 3.
Number 3, okay. Behind door number 3.
I was just wondering, what is the symbol for choice number D means? Like,
Which one?
Number D.
Or number D?
Yeah, like the symbol, what does it mean?
Okay, let me find it for you in my notes.
Google that for you.
Well, Googling would be a little bit harder because it's harder. Well, that may be possible. I think Google can now look up something using a picture.
Yeah.
So it might actually be able to do that. But I'm going to cheat because this is even easier. So, let me see. Which one is that? D?
Yeah.
Okay. So, keep going.
That's an improper circle.
It was one of the last things that we talked about.
It was
Not the
improper
very last
circle.
right here. Okay, so right here it says, B, if B is a subset of A, the expression B is a subset of A is true. But in this case, because there's a bar underneath, it's not a proper subset, it really is just subset of. So they can be the same, okay? A set can be a subset, can be considered a subset of itself. But if you want to be a proper subset, then you have to use this criteria, which means there has to be at least one element that is found in the superset but not found in the subset. Okay.
So as shorthand, could we compare that to greater than or equal to?
Yeah, pretty much. So one is kind of like less than or equal to, where they can be actually the same. The other one is just less than, strictly less than. Yep. All right. Any other questions about the little self-assessment?
There's only 6 questions.
There were only 6 questions. Yep. So let me see what score I'm gonna get. Finish attempt. I don't even know whether it will grade it because I'm not. I didn't sign yet as a student.
Yeah.
I didn't know.
Huh?
I don't think it's any grade out.
If
It
you
is
go
graded?
to
Okay.
go to grades, you can see what your score is.
Yeah.
Return to a 10.
Yeah. So you can see your score, but you don't know what you got wrong.
Right.
Right. But I just gave you the correct solutions, so that should be good. All right. Well, I'm glad that most of you did it because I can actually see who tried it out and who did not try it out. I think it's kind of important to get these things done, even though it might take you some time, because it's kind of a good way to confirm whether you got the concepts right or not. And the earlier you understand something, well, okay, maybe my understanding may not be correct, the better. Okay, the next slide talks about power set, which is actually a pretty easy, a short slide, but the concept itself can be confusing. Okay, so the power set of a set S is the set of all subsets of the original set S. Okay, so that statement by itself is not difficult to read, but it can be difficult to understand. Okay, so let's take a look at this, just one statement, and see what it means. Okay, so we are defining what is the power set of something. So a power set can only be a power set of another set S in this case. And the power set itself is a set, but it is each element is a subset of S. So it is a set of all possible subsets of a particular set S. Is that okay? All right. So I have some examples here. Okay, if you just go to this one here, this is the symbol for power set. It's just a weird way of writing P. If you right-click, show math as tag command, you can actually see how I enter that, which is a math cal, and then using curly braces, you'll put in the P. Okay, so that's how it's entered. So anyway, so within this set, the first thing people notice is, can we really have that? In other words, can we have empty set itself as an element of another set? Well, there's no reason why you cannot, right? So an empty set by itself can be an element of another set. Okay, there's nothing wrong with that. And then we have the three subsets that only have one single element. Miata is an element of the original set T, so a set of only Miata is a subset of T. Same thing with MR2 and Civic. And then we have all the subsets with only two elements. Okay, so I pick the three possible subsets with only two elements. And then we have the original set T itself. Well, T is a subset of itself because the requirement is not it has to be a proper subset, it just has to be a subset. So that's why T, the original set, is inside the the power set itself. Is that concept okay? Okay. So when you look at these concepts, but the next statement is kind of important too. So if the original set has n elements, then the power set of S has 2 to the power of n elements, because there are that many ways to create subsets. Yep.
So when we were doing the Cartesian product,
right,
we ended up talking that the resulting set itself, like
those are tuples.
Yeah, we get tuples in there
As elements, right?
And as elements, if we were to create a power set of such a set, would we concern ourselves with the ordering? Like, would we have the duplicates that we would have in there?
Within a set, the ordering is not important. Within a tuple, the ordering is important.
Okay, and since the tuple is actually just the elements themselves,
correct,
we would take them in with their order.
Within a tuple, you cannot exchange the orders. Yep.
What's the 2 there for?
Which one?
The 2, like what does
This
that have
one?
to do with that set right there?
Is 2 to the power of n. I'm counting the number of subsets.
Well, where does that 2 come from? Like, why wasn't it a 3 or a 4, Like,
because an element can either be in or be not in a set. That's why there are 2.
That's the only why.
Okay, so if you read on, there is more.
Okay.
Okay, so to read on, if that does not answer your question, we'll address it separately. Okay, so the most popular question is, what is a practical application of a power set? Why do we need to understand power set? Now, not that the following explanation is really the reason why we need to understand power set, but it is one application. Okay. So the application is to consider a 32-bit integer, and by this time, I'm hoping that everybody understands what is a 32-bit integer. Is that okay? 32 individual binary digits, okay, stuck together, and we interpret the entire thing as an integer. Okay. All right. So with a 32-bit integer, we have 32 binary digits, which is why we use the word bit, bit, because the b comes from binary and then the it comes from digit. Each digit can be a 1 or 0 because it's binary, okay, and they're independent to each other. So you cannot say, oh, this bit has to be a 1 because the other ones are 1s. Now let us consider a set of bit positions that have a value of 1. Okay, so let's take a look at this statement here. Okay. All right, so instead of giving you a number, a particular value, I'm going to give you a set of bit positions. Now, with a 32-bit number, the bit positions can go from 0 to 31. Okay? So I'm going to give you a set of bit positions corresponding to 1s. So all of these bits have a value of 1 and everything else has a value of 0. So that's how I'm going to define an integer in this case. So I'll give you one example. 35. Okay? 35 is a base 10 number. If I do not specify a base, it means implicitly it is a base 10 number. But you can rewrite 35 as 100011 in base 2. Well, you can double check. 1 plus 2, okay, let's see here. 1 plus 2, 4, 8, 16, 32. So 1 plus 2 plus 32 is 35. Okay, so this is just another way to represent the value of 35. So in this case, I am going to give you, so to represent 35 as a value, and I choose to use this representation, then I'll give you a set of 0, 1, 5, because out of a 32-bit number, these are the bit positions of the 1s. Everything else being zeros. Is that okay? So now you have to ask yourself, with a 32-bit number, how many integer values can I represent? How many unique integer values can I represent? It's 2 to the power of 32. Exactly. Whether it's signed or not is not even important. Okay, because you can either have all non-negative representations, so it goes from 0 to 4 billion something, or it can be signed where you can go from 0 to about 2 billion, and then on the other side go to negative 2 billion. But you still end up with 4 billion unique values that you can represent. Okay? All right. So that means we can also see the set of integers that can be represented as a 32-bit number as, guess what? The power set. The power set of basically a subset, excuse me, it's the power set of the set from 0 to 31. It's just this part here is really just a fancy way to say a set of 0 to 31 integers. Okay, each element x has to meet the following requirement. The requirement is x has to be an integer, and x is less than 32, and x is greater than or equal to 0. So it's a long way to spell out 0 to 31 as integers. Yep. Okay, any other questions? Any questions about power sets? Okay, no questions about power sets. Yep, go ahead.
Both those examples power sets or just the 0, 1, 5?
No, this is an element of that power set.
Okay.
Yeah, it's an element of the power set that represents all possible integers.
Yep. Can we do some more examples?
Pick another value.
22.
22. Oh, that's easy. That's too easy. Okay, so let's work out 22. Okay, so how can I represent 22 as bit positions of 1s in the 32-bit integer? Okay, that's what I want to do. What is the first step? What do you think is the first step?
It'd be like 16.
Conversion to base 2, right? Okay, so we are looking at 22 in base 10, and we want to express this as a binary number. So there are several ways to do it, but we can kind of do it intuitively. So we say, okay, the first one is 16, and we don't have any 8 because we have 6 as a remainder, so that would be a 4 and a 2. Okay, is that okay? So the first thing you want to do in the base conversion from whatever base into base 2 is to re-express the value as a sum of powers of 2. But the trick is you can only use one power of 2 exactly up to once, not more than once. Okay, but this meets that requirement because 16 is a power of 2. We only use it once. 4 is the same way. 2 is the same way. Okay. Is that okay? So the next thing you do is to convert it into powers of 2. Then you say this is 2 to the power of 4. That's 16. The next one is 2 to the power of 2, and then the next one is 2 to the power of 1. So I'm going to reline up everything so it's easier to read it like that. Okay. And then you can convert it into base 2 now, because 2 to the power of 4 is 1 followed by 4 zeros in base 2. Is that making any sense?
Can you repeat that?
Sorry?
Can you repeat that?
Yes. Sometimes I cannot, then I have to actually watch my own. I can actually do that. It's kind of like TiVo. I can. How did you call that?
Rewind?
Slipstream
Instant
rewind.
replay?
Instant rewind. Yes, instant rewind. I don't have a script to do it, but I can use VLC, replay the video file, and then just get to the point right before when people ask the question. And of course, I cannot alter the path the past this way, so I won't end up with a paradox or anything like that. Okay, so what I said was the value of 2 to the power of 4 is expressed as 1 followed by 4 zeros in base 2. It's kind of like 10 to the power of 4, otherwise known as 10,000, right? How do you write 10,000 as a base 10 number? 1 followed by
4 zeros.
4 zeros, because that's the exponent of 10. Okay, same way here. So that way I can now actually do the base conversion, so that I got 1 followed by 4 zeros in base 2. I have to use parentheses 2 to indicate these are now base 2. Okay, 2 to the power of 2 is 1 followed by 2 zeros in base 2. And this one is 2 to the 1, and then 1 single 0, okay, because it still has a power of 1. Okay. And let me just reline up everything again. I should have used a spreadsheet to do this, so I don't have to line up everything every single time. So there we go. Okay, now it's just a matter of adding. And in this particular addition, there's no case of 1 plus 1. Okay? Because if you line up all the digits, we either have 0 plus 0, or 1 plus 0, or 0 plus 1. So it doesn't even matter what base we're dealing with, because there's no carry. It's not possible to have carry in this addition. So you just pick out all the ones. Okay? But this is actually going a little bit beyond answering the question. But the answer is this. Okay? So to answer our own question, okay, I have to re-express this as bit positions of the ones. Well, as a set, 0 is not 1 because bit 0 actually has a value of 0, not a value of 1. Bit position 1 has a value of 1, bit position 2 has a value of 1, and then bit position 4 also has a value of 1. So a set of 1, 2, 4, 4, 1, 2, 2, 1, 4, however you want to reorder these things, is going to represent 22. Is that okay? Yep.
And that's always going to be the power of 2?
Yep. Well, I'm just using it as an example to make use of power sets.
Is there like a notation or something that says this set is representing binary, or is that just the standard?
No, it's just I'm just using it as an example. It's how you interpret the elements in a set in this case. Yep.
Professor, when I asked you the question with the second line, 2 to the 4, 2 to the 2, 2 to the 1. So that's 4, 2, 1 to the top. Is that always going to be 4? What I mean is power of 4.
That gives us the answer already.
Yeah.
I'm just finishing up the whole thing so that we can actually see the binary number itself. But if the objective is really just to figure out the set of all the powers of 2 that are 1s, that gives us the answer already. All right. Any other questions? Sorry? Yep.
So basically, you just do the powers of 2 and put them in a set, and that's what we get right now.
We are picking the powers of 2 that are 1s, or the ones that are present for a particular value.
Is there a reason you were doing that?
No, I just want to relate power sets to things that we already understand.
Just like binary.
Yeah, exactly. Because things inside the set can either be there or not. So that's why it's binary. That's why we have a 2 to the power of the elements of the set to come up with the number of possible subsets. Okay. Any other questions? No other questions? Okay. If there are no other questions, we are moving on to cardinality, which is, oh, somebody just sent me a message. Okay, cardinality is really just a fancy name of size of, okay? It's just, okay, how many things are there in a set? That's basically what it's asking. So in this case, when we look at the cars that I like, there are 3, okay? So the cardinality of that particular set is 3. The notation is just a vertical bar, so you have one vertical bar on the left-hand side of the set, one vertical bar on the right-hand side of the set. That becomes the cardinality symbol, and in this case, the answer is 3. Okay, so we will definitely come back and talk about cardinality a lot, throughout the semester. But it's a fairly easy concept to understand. Later on, we will look at cardinality even for certain particular sets where the number of elements is actually infinite. Because there are 2 types of sets where the number of elements is infinite. One is countable and the other one is uncountable. So you can have countable infinite and versus uncountable infinite. Sorry?
What makes it countable?
Can you enumerate all? Is there a way to map, a 2-way map? Is there a map that maps a set of integers into the set that you're dealing with? That is basically the question. As it turns out, some types of sets are kind of interesting. Even though we think it may not be able to be enumerated by integers, it can still be enumerated by integers in a clever way. But other types cannot be enumerated, like real numbers. They're not countable because you can always find it's just not possible because there's no way to map integers into real numbers. But rational numbers we can. Yep.
So it's kind of like whether or not a limit can converge or doesn't in math or calculus.
Whether
A limit can converge.
No, it's not. It's not about convergence. This is about can you
Similar.
Not exactly the same. This is discrete math, which means we are looking at individual things. The question is, can you look at the set of all integers and have a way to map the set of all integers into the set in question? And as it turns out, you can actually do that with rational numbers, like fractions and stuff like that. Even that can be done. You can also use integers to map into a 2-dimensional space with integers, like pixel locations. Yep.
So is that because there's no such thing as limits in computers?
The concept does not apply in discrete math. The whole point of discrete is...
No, but the fact that you are able to map it out is because that there's a given amount of space and that you can, fill up. So there's no such thing as a limit. That's okay.
It's not that either because integers, the set of integers is infinite by itself, right? There's an infinite number of integers. So the question is not whether it's finite or not. The question is, can you map one set to another set? That's the question. And we haven't really talked about functions yet, so it's hard to kind of describe that concept, what is mapping. So, but this will come back, okay? Cardinality will come back later on. Yep.
Not to drag this, but so you just said that the set of all real numbers is an uncountable set.
It is not countable. Okay. All right, so now we have the pigeonhole principle, and well, it's I just have to pick a pigeon, and this turns out to be my favorite pigeon. Okay, the pigeonhole principle is really kind of it's not exactly a part of set theory, but it can be applied in a particular way to sets. So this is the way we do it. Let's say there are n things to put into m non-intersecting sets. Okay, so we have a1, a2, am. Those are the individual sets, and then we have n elements to put into those things. So the statement is basically saying if there are more things than there are containers to put into, then at least one of those containers will end up to have more than one element. It makes perfect sense, right? I mean, it's just, oh, this is intuitive. Okay, prove it. Just because something is intuitive doesn't mean it's easy to prove, or that you do not have to prove it. Okay, so there are two things that I said. Okay, the first thing is it may not be easy to prove. Okay, well that we can set aside. Okay, because difficulty can be gauged. Well, cannot be gauged, but we can talk about that later. The second part of that statement was, it doesn't mean that you don't have to prove it. Something being intuitive doesn't mean you do not have to prove it. Okay, so why do you think that is the case? Intuition can be wrong, right? Can be wrong, and sometimes depending on what you use your intuition for, the consequences of using an intuition that turns out to be wrong can be very bad. Okay, so I'll give you one example from my own graduate school experience. So hopefully, professors at UC Davis are not listening. Well, for the most part, they can be listening because one person has retired, the other two did not get tenure, so they're all gone. So, okay, so I'm safe. Okay, I am safe here. All right. So when I was working on my dissertation, okay, it's basically a long mathematical proof of something, and my advisor told me about a particular theorem and go like, okay, this is the theorem, and you can start your dissertation assuming this theorem is true. Okay, well, that's not a bad thing. At first glance, the theorem made sense to me. Intuitively seemed to make sense. Okay, not a problem. And a few weeks into my dissertation, I thought about it a little more and a little more, and then I just have this uneasy feeling that it doesn't seem obvious to me that it is true. Okay, but doesn't mean that it has to be false. Okay, it just doesn't seem to me that it has to be true. So I went back to my advisor and told him that, okay, I just need to feel comfortable about this theorem, and I just want to see the proof. So my advisor said, okay, but just go back to this person's master's thesis because it is a part of that paper. Okay, this person supposedly has proven this theorem. Okay, so I dug it up, okay, and looked through the whole thing, and then the only thing that paper said about this theorem was, obviously. Okay, now in the world of rigid, or rigorous mathematics and stuff like that, obviously is a famous last word. So it wasn't obvious to me, okay? So it didn't answer my question. So my professor said, don't waste your time, just take it as granted, take it for granted, okay, it's good. I did not, I could not. So I spent about 1 week to come up with a counterexample. Now to prove something is wrong, you just need one counterexample, okay? But to prove something is right, you cannot just say, oh, it's right here, and it's right here. It has to be right completely, okay? So I came up with one counterexample. I took it to my advisor, and my advisor looked at the counterexample and go like, was it. That was it. That was it. So I went back to the computer lab, okay, the AI artificial intelligence lab, and told the other guy who was working on his master's thesis, not the one that said obviously, okay, this is another person. And I said, oh, guess what? You know, I just told my advisor that this theorem turned out to be not true. Oh, that guy just blew up. Because he was way ahead of me. He spent 2 years on his own research based on that assumption. and he just blew up and said, I'm gonna kill, substitute with the name of my advisor.
This is why we think you might be me, Ty. Just respond.
Yes, exactly. The fact that you found that entertaining.
Well, I don't know exactly what he had to do to adjust, in his own paper, but that was it. He could have asked, right? I mean, he didn't ask. I mean, so it's not really my fault that this happened.
My fault.
I just discovered it, right? I didn't come up with this. I just discovered it. I smelled something rotten and just dig around and go like, oh, it's this. Okay, but I didn't put it there. Okay, but the whole point is, something being intuitive seems to be right doesn't mean that it is, for one thing, and two, it doesn't mean that you don't have to prove it. So how do we prove something like this? The best way to prove something like this is counterexample, or not counterexample, it's called a proof by contradiction, which means you take the premise, the very same theorem that you were thinking that, okay, that has to be true, you negate it. And you say that that's not true. What happens if it is not true? Okay, so you work out an example, assuming the theorem is not true. If you come to a contradiction, then it means that the theorem is true. We'll get back to proof by contradiction later on in the semester. Okay, so in this case, we come up with the assumption that the pigeonhole principle is not true. But that ends up with a situation like this. It ends up with an expression of n is less than m and n is greater than m at the same time. And both of these are supposed to be integers. With integers, it is not possible to have n being less than m and also at the same time that it is greater than. This is a contradiction because it's a statement that is always false, regardless of the actual value of n or the value of m. Okay? So we'll come back and look at the proof by contradiction later on in the semester when we talk about proof techniques. Yep.
Okay, so the initial premise is that n is greater than m, right?
Correct.
And then so negating that is that n is less than m.
Or equal
Right.
to.
But would it
Because
be like
once-
wouldn't a negation just also be equals? Or
Sorry?
like I'm asking, can the negation be the fact that n could be less than or equal to? Would that also be a
No,
negation?
cannot be equal to.
Okay.
Cannot be equal to. So this is how it goes if you want to read the details. Okay, so let's say the pigeonhole principle is not true. Okay, this is the start of a proof by contradiction, is you negate the very theorem that you're proving. Okay, you just say that, okay, what if it is not true? Okay, so let's assume the pigeonhole principle is not true, but what does that really mean? It means if you have more items than there are containers, there is still a way to arrange it so that none of the containers has more than one item in it. Because that's exactly the opposite of what the pigeonhole principle is saying. Is that okay?
Yeah.
Okay. So that means there is a way to arrange all of these things where when you add up everything, it's just m because they're just m items. So when you add up all the items contained in all the containers, you have to come back with m,
Well, yeah.
right?
It's an item in every one.
But I already tell you that there are fewer containers than there are items.
Yeah. So the only way that would happen is if you don't put stuff in the container. If you leave some elements of n out.
But you did do that, but you're assuming that the pigeonhole principle is not true. So you end up with a situation where you can mathematically derive the expression and say that n is actually less than m. There are fewer items than there are containers, but that's not what we started off with. So when you combine that conclusion with what you started off with, the assumption that there are more items than there are containers, then you come to a contradiction because it cannot be true.
So then that means the premise that we started with is false, and that was the negation of.
Correct. So that means that means the negation of the theorem that you're proving leads to a contradiction, and as a result, it has to be true. That's my question. No? Okay. Yep.
When you come up with an E set only has up to one element, that would be the.
That's the negation of the pigeonhole principle. Because in the pigeonhole principle, when you have more items than there are containers, then the theorem says that at least one container has more than one item in it.
Yeah, but when we say an E set has only up to one element, that's nowhere in the pigeonhole.
That's the negation of the pigeonhole principle. Because the pigeonhole principle says right here, so it says at least one of the container has to have more than one item. So the negation of more than one item is less than or equal to one, or up to one item.
I think I missed. It's the next one. Why is it M? Why is the cardinality of all this is M? Assuming that there's one element per A. In this case, AK. Each one has one, and the third line says must be less than or equal to M. Where do you come up with the cardinality of AK in this case?
AK in the sentence that is being highlighted?
No, in the next paragraph.
In the next paragraph.
The fourth line, the third line in the next paragraph.
You mean this one here?
Yeah.
It's because of the negation of the theorem, because of this part here. Each set only has up to one element. Because that is the direct result of negating the pigeonhole's principle.
Okay, so now each group or each set has at least one element.
No. Up to one.
Up to one element.
Can be zero, but it can only have up to one. So that means when you
there could be more, so that's why you can't use that.
right. So when you add up all the items in every single container, and there are only m containers, so when you add up all of these, it can only be up to m.
Yeah, can we draw 4 containers, please?
Okay.
We need visual.
Visual. Okay. You need visual. Okay. Okay. So the pigeonhole principle means containers. Okay. 1, 2, 3, 4 containers.
Let's say we have n elements, 3 for instance.
No, it's
So
like,
like-
no, the pigeonhole says we have.
But you have to
5
start off with more items than there are containers.
Yeah, we're going with the negation.
But that's not what you're negating. What you're negating is the statement that at least one of these containers have to have more than one items. That's what we're negating. We still have more items than there are containers.
Show 5 items, maybe, because we only have the containers, we have to show how many items we're trying to put into that. So the n
But
is.
this part cannot be seen using an example because the theorem itself is actually true. So the theorem is by itself a conditional statement. It's by itself an implication. The implication states that if you have more items than there are containers, then at least one of the containers will have more than one item.
I understand. Now let's do, because we're trying to prove that, right?
We are trying to prove that implication is true.
It's true.
So the first thing you have to do is to negate the implication,
Okay.
and then you have to prove the consequence of the negation of the implication leads to a contradiction.
So let's negate it, and let's put elements in those containers, just 3 or 4 elements, because that's what
We
we're
don't negate the
getting to.
conditions, we
Yeah, we don't
negate the proof.
Okay, we negate the implication itself. Okay, so I know this is really kind of getting out of the flow of this class, but I since we are talking about this, and we already know what the implication is, right?
Yeah.
So let's do that. Implication is kind of like P implies Q. That's an implication. I think it has a more echo here because the speaker is right there. Okay, so I need
So I think it
to
should be.
either turn it off or.
Use the sample board.
Hmm?
Use the sample board.
Yeah, I can turn on more lights.
Destroy the previous arc.
Destroy the what?
Previous arc.
Previous part.
Yeah, I think
Oh,
we're good on this.
Okay. P implies Q. That's an implication. So in this case, what P is there are more items than there are containers. Q is saying at least one container has more than one item. Is that okay? All right, but that's not even the focus. The focus here is how do we negate it? In other words, how do we put a negation on top of this? Tag, you never talked about anything like this. Maybe not, but I did define implication using normal logical operators. Can someone remind me what is P implies Q in normal, like negation, conjunction, and disjunction operators?
It means
P and Q equals true.
No,
so it was not P.
not P or Q. Okay, that's implication. Okay, in other words, P implies Q is exactly the same thing as not P or Q. They have the same truth table. Is that okay? Did you guys read the notes? Because I can check that using the Moodle log. It doesn't have to do it right now because I can check the dates. Okay, but this I can negate, right? Okay, let's see how we can do a negation here.
Okay, so then it would be P.
Okay, how do we put a negation on top of this? How do we turn things around and whatnot? And that's called which rule are we using? De Morgan's law. Okay, De Morgan's law. So De Morgan's law says, if you take a negation of the result of a disjunction in this case, you can quote unquote distribute the negation into the items of the disjunction. But then you have to turn the disjunction into a conjunction. Okay, so the end result becomes the negation of the negation of P, which is distributing the negation onto this term, negating this term here. But we have to change the disjunction into a conjunction, like that. Okay, that's De Morgan's law. The negation of a negation cancels out. In this case, that is not canceled out. Okay, so now we have the actual negation of an implication. Yep.
And if we negate and, it's going to become more.
Correct.
Okay.
De Morgan's law also works the other way. So if you have a conjunction inside the negation, it would be, you can distribute the negation, but then you will turn the conjunction into a disjunction. You just flip it to the other side. Okay, this is called De Morgan's law. It's kind of mechanical. Okay, but remind me what is P in this context?
That there are more elements.
There are more elements than there are containers. So this means there are more elements than there are containers. What is Q?
That there's more than one item inside of it.
At least one container has more than one item. What is the negation of that?
That
None of them have more than
All containers have
Up
At
to
most
up to
one.
one element. So is that okay? I mean, is that working out okay now?
Yeah.
So let's spell it out. Okay, so P is basically saying more items than containers. Okay, that energy. Q, not the negation, the Q itself is saying at least one container has greater than one elements or items. Is that okay? That's just Q all by itself. So that means the negation of Q, the other way to saying the negation of Q is to say all containers have less than or equal to one elements. Is that okay? Does it make sense? And that's how we end up with the contradiction.
studies are bad.
Well, it's really important that I dig into the details, to really give you the step-by-step, stuff that you need in order to work this out.
Is that good or bad?
It's math. That's all I'm gonna say. It's math. It's not good. It's not bad. It is math. All right, but we will come back and see this again. Okay, this is not the first time. This is the first time, but it's not going to be the last time that we see this sort of logic. Well, it is logic. I mean, in a way. Okay, the next section talks about. Let me see, what time is it? Ooh, almost forgot. I keep forgetting this stuff. Because it is kind of vertical. Okay, so go ahead and sign in. All right, so the next slide talks about, what does, set theory have anything to do with programming? Okay, the first one, I'm pretty sure very few people, if any, in this class has any idea of what is the select call. Okay, the select call is actually one of the most basic stuff in systems programming. If you are going to Sac State to get a bachelor's degree in computer science, you will probably have to take what they call systems programming. Okay, there's a class called systems programming. I'm not sure whether they teach this concept or not, but as far as I'm concerned, this is one of the core concepts of systems programming. But anyway, in this class we don't do systems programming, but the concept of using a set is actually important in that type of context. And it's actually low-level, kernel level type of programming. So I'm not going to get too much into the detail of that. I think most of you know the template in C++. Okay, so you can implement what is also known as a set in C++. In other programming languages, most scripting languages like Perl, PHP, and Python, they also have a concept of either a hash or a map, depending on the language, and it behaves just like a set. Okay, you can have. It will check whether something is already in it. If it's already in it, it won't store a duplicate into the container. But if it's not already in it, then it will store one. Okay, which is the behavior of adding an element to a set. This part I just added like last night. There are plenty of algorithms that make use of the concept of set theory because it's just an easier way to express an algorithm. Okay, so mathematically speaking, the notation of using set and set-related operations is actually very handy. It's just that most programming languages do not have it as a built-in feature, and that's why you don't see it in C or C++ by itself. It's a template, but templates are kind of iffy, right? I mean, it's like an afterthought, of C and C++. But it is going to be useful. Okay, the concept of a set is going to be useful. And now we move on to functions and relations. Are there any questions before we start on functions? Okay, no questions? All right, so we're going to start on the introduction of functions. A function is a map, basically. Okay, so a function is really a map. And for no particular reason, I'm just skipping to this example here. So for no particular reason, I define function f as follows. F of 2 is 25, f of 5 is 67, and f of 1 is 102. And those are the only three values you can feed to the function f and get a result. Okay, does this function do anything really useful? Not to my knowledge. Is it a function? Yes, it is a function. Okay, so, but using this as an example, then I can tell you one way to write function f. Okay, to describe function f, I can describe function f this way. Okay, so in this notation, this is the name of the function or the symbol that you want to use to denote that particular function, followed by a colon. Okay, which basically says, okay, f has the following property. The first set is called the domain. These are the values that can put into the parentheses when you say f of something. So these are the only values that can go into the parentheses. And then we have a right arrow, a single right arrow. And in this case, I use a single right arrow to means map to, okay? So it maps to another set. In this case, 25, 67, and 102 are potential results of applying function f. Okay? Is that okay? Yep.
So that's the name of the second grouping, or second set is?
It's called a codomain. Codomain, or let's see, the domain versus the range. Yep. But in this class, I call it a codomain. Yep.
Does the order matter?
Nope, because it's a set. Remember, everything in curly braces, the ordering is not important.
Okay.
Yeah. So the other notation is this one. It's just harder for me to type, so I don't use it as much. Is 125 as a set maps through function f to 25, 67, and 102. Yep.
So because ordering doesn't matter, if we only got that notation, we wouldn't know what one maps to?
That is correct. It does not tell you the actual mapping. It just tells you what is the domain and what is the codomain. But it doesn't tell you exactly how it is mapped. That is correct. All right, so given this, okay, if I want to tell you the exact mapping, this is how I would do it. Okay, well, this is one way to do it, is to spell it out. Okay, so let's go ahead and take a look at this expression first. So we'll start with this one here. We already know what this symbol stands for, don't we?
Cartesian product.
Cartesian product, okay? So a Cartesian product would end up, in this case, with how many elements? Just the Cartesian product itself. How many elements do we have in 9 items? Because we have 3 in one, 3 in the other one, so we have ended up with 9 elements in the Cartesian product. The function itself does not make use of all 9 elements. Okay, it only has to use 3 in this case. So that's why the function is a subset. In fact, it is a proper subset, but I'm using just subset here. So the function is a set of 3 tuples, but this particular set is a subset of the Cartesian product of the domain and the codomain. Is that concept okay? So there are 6 items in the Cartesian product that is not of any use in the function itself. Is that okay? All right. Yep.
What is that in between the Cartesian product and the first, the little like C with a line underneath it? What is that?
This one?
So yeah.
Subset of.
Subset of. So what if it doesn't have a line under it?
Proper subset of. Yep. All right. So these are just terms. So in general, not using a particular example, I would express a function that has a name of f. And x is the domain, y is the codomain, and the arrow points from the domain to the codomain because it's a map, but it's a one-way map. In general, it's a one-way map. It is also true that f has to be a subset of the Cartesian product of x, y. Now, in general, I cannot say it's a proper subset of. I can only say it is a subset of, but not a proper subset of. Why do you think that is the case? Because x and y can be singleton. They can be, each one is a set of only one item. Now remember, if x only has one item, and y only has one item, what is the cardinality of the Cartesian product?
1.
Exactly 1. So in that case, the function has to be just a subset of, because it is exactly the same as the Cartesian product. And that's why in general, I cannot say it's a subset of. Even though in most cases it is a subset of, but there are cases like in this special case when x only has one element and y only has one element that I cannot say is a proper subset of. So that's why in general, I can only just subset of. But you cannot just say, okay, we'll just pick some elements out of this Cartesian product and turn it into a function. Okay, Okay, only certain subsets can be a function, not all of them can be a function, because there's this particular requirement here. Okay, so I will start off with the clumsy way to describe it, and then we'll come back and use a more intuitive way to describe it. So let's take a look at this mess here and see what it means. Okay. All right, so we are looking at a particular set. Okay. Because we're looking at the cardinality of a particular set. What set are we talking about? Well, what is considered an element of this set? Well, each element is xy in parentheses. So that means this can only be a set of 2 tuples. Is that okay? That's the first restriction of what can be in this particular set. Go ahead, George.
Is there a bar around?
There is. But I'm reading it from the inside out. Okay, I'm reading it from the inside out. So the first thing I want to do is to say, okay, what can be considered an element of this particular set? Well, first of all, we know each element is a 2 tuple. Okay, so what are the other qualifications of each element? Well, there's only one. xy as a tuple has to be an element of the function f. In other words, when we look at function in this class, we are not looking at a function like sine, cosine, and stuff like that, where you give me a value, I'll give you a result. Okay? We are looking at a function as a set of tuples, 2 tuples to be exact. So in this case, xy has to be an element of the function f. Okay? So this is a set where we only have elements coming from f. And then we apply, okay, these are the curly braces, which basically says, okay, this is a set of 2 tuples, and each 2 tuple is inside the function f. But we already fixed what x is, because we say that for any element x of the domain, okay, this has to be true. What is the cardinality? The cardinality of this set has to be exactly 1. Okay, so I guess the more English way to say this is for each element of the domain, for each element x of the domain, it has to have exactly 1 element corresponding to it in the function. Cannot be 2, cannot be 0, it has to be exactly 1. Okay. So just to test whether you get this concept or not, I'll give you a few examples. The first one is this one here. So with this one, how do we know it is a function? Does it meet that requirement? For each element in the domain, it only has 1 element in the function corresponding to it. Does that meet that requirement? Can someone give me an example where we still have the same number of elements, but it's not a function anymore? Right. Well, you cannot repeat a tuple because 1, comma 1, 0, 2 as a tuple. If you repeat that, you cannot repeat it in a set. But you can say 1, comma 25. Instead of 2, comma 25, I turn it into 1, comma 25. Then it's no longer a function because it breaks the rule in 2 ways. Which 2 ways is it breaking the rule of becoming a function?
There's not a unique. It's not unique anymore. I guess it's like a 1 to a 25 now. Like
right, exactly. So 1 element now has 2 elements in the function. 1 element in the domain now has two elements in the function, and the other one has none.
Wouldn't that be like if that was the case? Wouldn't it be redefining itself? Pretty much.
Okay, let me give you. I'll just write it out so this way we can see it. Because if I just say it's harder to visualize. Okay, so if I say that f is in curly braces 1, comma 102. 1, comma 25, and 5, comma 67. This is not a function anymore. Okay, and I'm going to say why it is not a function anymore. Okay, it's not a function anymore because now there are 2 elements in F corresponding to 1. And 0 elements in F corresponding to another element in the domain, which is 2. So it breaks the rule in 2 places, not just 1. Yep.
So according to Pigeonhole, there has to be less elements in the codomain.
Nope. There's no rule saying that. There is no rule saying that you have to use everything in the codomain. So you can have lots of stuff in the codomain, just not used. Because the rule is, for every element in the domain, it has to be mapped to something in the codomain. Well, they can all map to the same thing. And then you have everything else being in the codomain not used. That's perfectly okay. Okay? It is still a function. Okay? It doesn't have certain properties that we'll talk about later, but it is still a function. It still meets the requirement of being a function. Any other questions?
What if it?
Oh, sorry. Okay, go ahead.
No, you go.
Okay. Why does it fail the second condition, 0 elements in F corresponding to 2?
Because the requirement is there has to be exactly 1 element in the function for each element in the domain. 2 is still in the domain.
Okay. So it's just not represented on the screen. It's still
Correct.
Okay.
Yeah. Go ahead.
So what
No,
if,
no, no.
What if it's
Yeah,
an
go
empty
ahead.
set then?
Hmm?
That's actually part of his question. What if it's
Oh,
an
what
empty
if it's
set?
an empty set? Okay, that's a good question.
There would be 0. Then there would be 0 elements.
Then you're breaking the rule again.
You
Okay?
are?
Because the domain, okay, you're not changing the domain, right? The domain is still 1, 2, 5, right? Right?
Yes.
That is still your domain.
Correct.
So the rule says, for every element in the domain, there has to be exactly 1 element in the function corresponding to it.
So
if your function is an empty set,
Then
then
it's not considered a function.
then it's not a function.
Okay,
Empty
so-
set is not a
Okay,
function.
empty set's not a function.
Unless your
All empty sets.
domain is an empty set itself, then the function can also be an empty set. Okay, that was another hand. Go ahead.
Yeah. Isn't that impossible to get that kind of set from a Cartesian product, anyways? When it's like a
No, that's a proper subset of the Cartesian product.
The subset of the Cartesian
subset.
product.
Yeah.
Which makes sense.
Yep. Go ahead.
I was just gonna comment on that because of hyperbolas and stuff like that. In Cartesian coordinates, you can have 1 x value that's worth 2 y's.
Yeah, kind of like that. Yep.
Makes sense.
All right. So let's check out the time. We are running out of time, so this is where I'm going to stop today. So read ahead of me, okay? So read ahead of me and find out what are the 3 properties of a function before Thursday. Okay? Alrighty. There's no homework except for the self-assessment. So I did go through it today in class, but if you haven't done it, go ahead and do it.
Are those the next slides though? In the 3 properties?
Yeah.
Okay.
Yep. Just read it in order.